Hello everyone, welcome to the 11th video lecture series of our differential geometry course. Today I'll go back to chapter 2 and study section 2.7, which is called connection forms. These are fundamental objects of modern differential geometry, and we will need it in our study of curvature in chapter 6. We had skipped this while we were studying chapter 2, but now we need them, so I come back and I'll cover these two sections, section 2.7 and 2.68. Sorry. We start with the lemma. Okay. So let E1, E2, E3 be a frame field for R3. So they are vector valued functions. They are all orthonormal. So that's why we call them a frame field. For each tangent vector V to RP through R3 uh, at the point P, at a point P, let omega ij V be the following expression. So it is the covariant derivative of EI along the vector V. This is a vector. And then we just take dot product of this with the frame element EJ for all IJ from 1 to 3. Okay, this is not a statement, just a definition. Statement is the following. Then each Wij is a one form, and they are skew symmetric. Okay, these one forms are called connection one forms. The connection one forms for the frame field E1, E2, E3. Okay, now let's see the proof. Proof is simple. We just apply the definitions and perform standard operations. Okay, so let's see why this is a one form. So it should be linear, right? So it should be at each point, it should be a covector. Well, by definition, this is just covariant derivative along the vector AB plus BW of the field EI, and then we take dot product of this with EJ, and all these things happens at the point P, of course, and here V and W are tangent vectors to R3 at the point P. All right, well, covariant derivative, we know that this is linear, so I can write this expression as A times covariant derivative of EI plus b times the covariant derivative of ei dot product ejp, and then we can further write this like this: ejp plus b times covariant derivative of ei dot product ejp. Well, this is just a times wij of v, and this is b times wij of w. Therefore, and thus wij is a one form. For skew symmetry, we consider the following. For the second statement, which says that wij is skew symmetric, note that we have this: 0 equals this, right? This is depending on I and j, it is either 0 or 1, a constant function in any case. Therefore, its derivative along the vector v is 0. But I can write it like this: ei dot ej. And then we know that we can apply Leibniz rule. And this means what? This is just covariant derivative of ei and then dot product with ej plus covariant derivative of ej dot product with ei. However, this is just wij of v, and this is wji of v, and this finishes the proof, right? This implies that wij, this is true for all v, right? And for all points, of course, but in particular, this means that wij is equal to w minus wji. All right, so this finishes the proof. Actually, a consequence of this result, we have this. Let me state this as a theorem. For any vector field, V on R3, we have covariant derivative of EI along the vector field V. So this is a this is another vector field. This vector field is just equal this. This vector field, I feed the one form with the vector field. I get a number at each point. So this is a function on R3. And then I multiply these functions with the elements of the frame. So I get a vector field. And this is equal to this gadget. This is, of course, almost trivial. Well, by definition, we have this: wij of v is equal to ei dot product ejp for any vector, for any p in R3 and v in the tangent space. Okay. but this already shows that. So whatever this vector is, its jth component is this, right? Since this E1, E2, E3 is a frame, so it's an orthonormal basis at each point is a frame. We see that this gadget is equal to Wij at V. So this is for any vector V, and then E Ej, sorry, P. But this is true for all P and V. Well, this implies this is true for the vector field. So summation over J here, of course, Wij V and then Ej. All right. So this finishes the proof. Here we have an important remark. Well, since the one forms are skew symmetric, we have diagonal terms equal to 0 because Wii is equal to minus Wii, therefore Wii must be 0. Thus, the matrix of the matrix Wij of one forms, connection one forms, connection one forms is what? Well, let me write it like this. Let's say this is W. So I have W11, W12, W13, W21, W22, W23, W31, W32, W33. Okay. Well, I have W11, but it is 0 because of this. And then I have W12 and then W13. W21 is just minus of this. So let me write like this, W12. And then I have 0. And I have W23. And then I have W13 here minus W23, and this is also 0. Okay, so connection one forms are determined actually by just 3 terms. Okay, these 3 terms. Uh, Even though initially we had like 9 terms, actually the relevant ones are just these 3 terms. Okay. All right. Now we start again our okay. Start with our frame field. Given a frame field E1, E2, E3 on R3, write EI in terms of standard frame field of R3. So Ij uj, where uj, uh, where aij is of course what? Ai times uj. Okay, here where uij is this. So u1 is the frame field 1 0 0 at all points. u2 is 0 1 0 and u3 is 0 0 1. All right, standard frame field. So I have some functions. Okay, aij's are some functions. The matrix whose elements are this aij's, the matrix aij, let me write it this way, a of aij is called is called the attitude matrix of the field E1, E2, E3. Okay. Well, these are functions. So each aij is a function, right? From R3 to R given by this, right? At any point, it is equal to this EIP dot EJP. Well, this is a constant function. So it's just the dot product of these two. Therefore, I can take their differentials. We define the differential of A as the matrix of one forms, namely DAIJs. Okay, here's the definition. So DA is just I just take DIJ, their differentials, and write this is a matrix. Okay, why we did this? Because it will appear in our considerations. Well, assume the above setup. So I have the frame field one forms and then the attitude matrix. The statement is this. The matrix of connection one forms is equal to the product of the matrix dA times the transpose of A, where this is a matrix multiplication, where matrix multiplication is done using uh, uh, okay, here these are actually functions. Okay, I don't need this. I'll need this later. Okay, let me stop here. Let's see then. Okay, or equivalently. Let's write this equivalently. Wij, the ijth entry of this is what? Okay, ijth entry of this d I k, and then so this is the one form, and then kjth entry of the transpose. Kjth entry of the transpose is jkth entry of A, where summation is over the index k. But we write it usually like this because this is a function, this is a one form, so this is ajk dark, k from 1 to 3. So this is the statement. Let's see why this is the case. Well, we have this definition, right? This is the equation which defines the constant ai case, k from 1 to 3. Now let's compute wij at any vector v. By definition, this is just the covariant derivative of ei dot product ej at p. Here, v is a point in the tangent space of R3 and p is any point. Okay. Well, this can be written like this. So covariant derivative of, instead of ei, I will write its expansion in this standard frame, k from 1 to 3. So I'll just take derivative of this and then product with ejp. Well, what is this? These are functions, these are uh, elements of the frame field, standard frame field, which are constant frame fields, right? This is a constant frame field. And here I apply Leibniz rule, of course. First, linearity of this operation, and then I have this aik uk dot product with ejp. Okay, I can write it like this. Yes. Okay, so what is this? This is just summation. Here we apply Leibniz rule, covariant derivative of aik dot product with uk plus aik. Well, covariant derivative of aik is of course just okay. Let me keep it here first, and then here I have k from 1 to 3 aik, and then the covariant derivative of uk. This is a function. Covariant derivative means just the usual derivative of this function along the vector v. Well, that is just equal to the following. I take the differential of this and compute this at the vector v. This is just this is a scalar function times uk plus but here note that this is a constant field, therefore this derivative is 0. So I just get this. Uh, okay, well, I shouldn't forget that this is multiplied with EJP. So this thing is multiplied with EJP. Well, so this is K from 1 to 3. DAIKV UK, and then dot product of this. What is this? This is just L from 1 to 3, A, J, L, and then U, L. Okay. Well, this is just summation over K and L, and then I have DIK, DJL, UK dot UL. But we know that this thing here, okay, let me just continue. Let me just do this. This expression here is just Kronecker delta KL, and it is either 0 or 1. If they are the same, it is 1, otherwise it is 0. So this double summation reduces to a single summation. Let me write like this from 1 to 3, because if L is different than K, this is 0, so I get nothing. So I have only non-zero terms when L is equal to K, so I have just J and K. And this finishes the proof. Okay. Here I forgot. Here I have, sorry, V and then A, J, L. Yes, so V, A, J, L. But this is true for all V. Hence, you see, uh, for all V, this one form is equal to this one form. Therefore, hence, hence Wij is just summation over K, DAIK, one form times this function. Not JL, JK. Yes, JK. All right, so this finishes the proof. Okay, now we will now consider section 2.8, the structural equations. As I said at the beginning of today's lecture, these are actually uh, standard tools of modern differential geometry. So they are not just specific to the study of surfaces. Their higher dimensional versions are used in modern geometry. So this is just the special case of modern differential geometry. All right, now we will define dual one forms for any frame field E1, E2, E3 on R3, we define the dual one forms theta 1, theta 2, theta 3 as the objects theta. So this is a one form, and it is just v dot eip. Okay, it is clear that this is a one form because you take this vector field and dot it with v. This quantity is linear with respect to the v coordinate. Therefore, this is a one form. Okay, so for any v in tp r3 and p in r3. All right, let's do one immediate example. Consider the natural frame. Frame field uh, u u1, u2, u3. Then what is the corresponding one form for ui? Well, this is just v times ei, but e just u in this case, so uip. So what is this? This is the vector, let's say v1, v2, v3 at the point p, and this is just well, depending on which one we have, uh, it is either 1 0 0 or 0 1 0 or 0 0 1. So this is just vi, but we have another vector, we have another one form which uh, gives us the same value, uh, which is just dxi, right, v, right? Okay, this is just vi because this is just the derivative of the function xi along the vector vi, and it is just vi. For any v, we see that theta I is nothing but dxi. Okay. All right. So dxi is just the dual vector field for the standard frame field or natural frame field. Now, next we have a lemma. Let ei and theta I from 1 to 3 be as above. Then for any one form on R3 uh, has a unique expansion like this. So I can write this one form as a combination of theta i's, and here are the coefficient functions theta I. Proof is of course immediate, well, as from the definition. Well, let's see. Take this expression, right? This is a one form, and evaluate it on the vector v. Well, this is since because of the linearity, I can write this as okay, but this is just phi of theta I v times EI. Yes, these are just some numbers, and okay, uh, and this is equal to for any vector field V. Hence we are done. Hence this is just okay. Yeah, these are some functions multiplied with one forms, and then we evaluate this on a vector field. So it is equal to this one, but you know the definition of this is just I take this and compute on this vector field. Okay. Now let's recall our matrix A. Recall that. Recall that the matrix A, which was you the matrix with entries aij's, is defined by the equation. What was the equation? EI is just aij uj, right? Summation over A. So if I combine this with the above, we get this. Hence, theta IV. What is this? This is by definition V dot EIP, but this is just V dot EIP is just this AIJ UJ summation over J, and this can be written as uh, summation AIJ V dot UJ summation over J, but this is equal to just the uh, we just computed this above. This is just dxj v. Therefore, hence, so that we obtain the following. We obtain theta I is equal to aij dxj. So the dual one forms corresponding to this frame field, dual one forms, is given in terms of this matrix Aij and standard one forms corresponding to the natural frame field. Okay. All right. We have also the following. Moreover, since Aij is equal to AI times Uj, which is equal to theta I of Uj, we have theta I, so this can be written also like this, summation over j, theta I of Uj times dxj. Okay. All right. Now we have the main result of this section, Cartan structural equations. Cartan structural equations. They are, these are combining the derivatives of the one forms we defined so far in terms of these one forms again. So let EI, theta I, and Wij as above. Frame field dual one forms and connection one forms. Then we have first this, the first structural equation. What is this? Or equations. They give us derivatives of the dual one forms, and these dual one forms are given like this. I take connection one forms and then wedge them with the theta j's. The second one, the second structural equations, and they give us the following Wij's. So derivative of the one form is given in terms of Wik, Ik, wedge product Wkj. These are important ways that because we have this frame field. Using this frame field, we define these objects, one forms and connection one forms. These are one forms. Of course, since they are one forms, it is natural to take their derivatives and obtain two forms. And these equations tells us that their derivatives, exterior derivatives, are again, of course, they will be given in this in terms of these objects, because this is a two form and they form a basis for one forms and so on. But how they will be represented. Here is the equations which describes the exterior derivatives of this one forms. So these are very important tools. It is not easy to appreciate these formulas at first, right? They look complicated and so on, but you will see that they are very helpful, and as I said at the beginning, they are very fundamental objects of modern differential geometry. Proof, well, we just apply the definitions and use the results we obtained so far. Okay, now we obtain this object here. Theta I is given in terms of aij like this. I'll take this. Recall that we have this. Theta I is equal to summation over j aij and dxj. And this can be written as matrix multiplication theta equals a times dxc, where A is the matrix, the attitude matrix, and uh, theta is this matrix, theta 1, theta 2, theta 3, dual one forms, and dxc is the matrix of one forms, dx1, dx2, dx3. Okay, it's easy, to see this from this equation. All right. Now take derivative of this theta. D theta becomes what? D of a times dxc. Here, of course, these are just functions. Sorry, these are one forms. These are functions multiplied with one forms. How would you take the derivative of this? Well, I just take the derivative of differential of each entry of this matrix multiplication. Each entry is a sum of terms aij times one of these. So when I take the derivative, I just apply Leibniz rule. I take the derivative of ai, wedge product with this term, and then plus this plus derivative of this. But the derivative of the xi's are zero because they are one forms, single one form, so they're already derivative of something. So when you take d of this, you get zero. So we get this uh, derivative of the uh, attitude matrix, I mean derivative of each entry, wedge product. So I write dc, but this means wedge product actually, minus no, it should be plus because yes, this is a function, not one form, a times exterior derivative of the one form dc, but this is just d squared c, and this is just 0. So we get dA times dx. Here, the product of two one forms. Of course, when you compute the entries of this matrix multiplication, you take a wedge product of the entries of this matrix and this matrix. Okay, um, the book doesn't put wedge notation here, but you may put it here, or simply we just write it like this. Okay, but we don't forget that these are one form, so when you take the product, you take the product as if they are one forms. Therefore, you have to use wedge product. Okay. However, for simplicity, we don't put this wedge here. Maybe I put it in a different color so that you okay. We just write it like this. Okay. Keeping in mind that they are multiplied as one forms using wedge product. Okay. Okay, so we are not done yet, of course. This is equal to what? So dA, I put uh, between these two matrices this gadget, A transpose times A. And then I have this matrix. And I'll explain why I can do this in a minute. I can write this dA times A transpose because matrix multiplication is associative, A times C, and this finishes the proof because this is, we know that the connection matrix, connection one form matrix, and this is by definition the matrix theta. I can do this because, you know, the matrix, the attitude matrix A is orthogonal, so that A transpose times A is just identity. And why is that? Explanation for this: A entries of A, right? It was defined this way: Aij, Uj. So this Aj is just actually uh, okay. Maybe I should write this. Okay. So let me write this in more detail. Uh, since Aij is just Ej dot Ui, okay, or I didn't, let me write it this way. Ei is Aij Uj. We see that the attitude matrix Aij is the base change matrix from the orthogonal uh, base, orthogonal orthonormal normal base ui or ui's to the orthogonal basis ei's. Okay, let me write it this way. That's why, since this is the base change matrix from one orthonormal basis to another orthonormal basis, orthonormal, uh, it is an orthogonal matrix. Therefore, A dot A transpose is equal to identity. So this proved the first, uh, claim first structural equation, right? Yes, so the matrix W is multiplied with this. Okay. For the second one, well, we proceed as follows. Well, d omega is just d of omega was a, sorry, a transpose, because omega was this. So this is just d squared a, and then a transpose minus dA, and then dA transpose. But yeah, this is 0. If you take derivative twice, you get 0. Therefore, this is just uh, minus dA, dA transpose. All right. Okay, I can write it this way. This is just uh, minus dA. I put A here, no, A transpose here, and then A here, and D A transpose here. Noting that this product is identity, right? This is just identity. So I can just insert that in between the two terms. Well, this is just uh, d of, okay, so this is minus, this is just omega, and then sorry, it's minus omega, which okay, uh, instead of this I can write, okay, I just switch, yeah, let me write this, ADAT, right? Yes. So here I have minus. Now I okay, write this as minus. Wait a minute. What was omega? Omega was uh, yeah. Wait a minute. Yeah, it should be like this. Sorry. on my notes. Okay, yeah, yes, the a okay, let me do it this way. Minus of this, and then minus d a transpose uh, a transpose uh, a and dA transpose. So here I use the fact that this is identity, and then we do this. Uh, so uh, omega is so here this is just okay. Omega is a uh, uh, wait a minute. Omega was yeah. So omega was dA dot A transpose. So this is just minus omega, and then wedge product. Here I have wedge product, of course, of dA A transpose. So this is minus omega wedge product with omega transpose. But these are one forms, so I can just write it like this. Interchange the two, and I obtain this. Okay. All right. So this finishes the proof. What else? Okay. Okay. All right. So this corresponds to what? This corresponds to, of course, the statement summation over. Okay. Uh, right. This means this is equal to saying that this is omega transpose. Okay. Because ijth entry is ik and then kj. Wait a minute. uh, d a transpose a d a uh, okay, dA transpose minus dA transpose. I put this inside. Yes. Right. Omega is this. Yeah. Okay. And then we have this is just omega, and this thing is just, oh yeah, this is when you take transpose, you get transpose of this times, sorry, this is not correct. I should be more careful. Okay, let me do it this way. Now this is uh, minus uh, dA A transpose, and then A D A transpose. This is minus omega. What about this? I can write this as dA and then A transpose transpose, right? When I take transpose, I get this and then this gadget. Yes, so this is just uh, minus omega times omega transpose, but omega is, right, what is d omega? D omega is so no, omega is this, uh, okay, so this is equal to this gadget because omega is skew symmetric. Okay, yes. All right, so this finishes the proof. Sorry about that. Now I have an example. Let me do this example. Uh, okay, let's see how much time do I have. Oh, I don't have time actually. Uh, Maybe I do it next time. Okay, let me stop here for today. Next time I'll do one example and then we will skip to we will pass to chapter 6. All right.